Hi, hello again. Feels like I just did this, because I just did. I finished recording that other video, and then I forgot, or I remembered that I forgot to address a concept, so we're going to put on our thinking caps, and we're going to talk about one last quick thing with bounded integrals. Alright, so, I am going to, this is kind of a big concept that I just totally forgot to do. Let's define some integral from bounds a to c, right, of, I don't know, f of x, right, dx. Now, there are two things we can do with this that I kind of forgot to talk about. Let's say f of x is in fact some polynomial function of multiple terms, say x squared plus x, right? Now, I claim that this integral here will also be equal to the integral from a to c of x squared dx plus the integral from a to c of x dx, right? And now this is the same thing with our unbounded integration, right? So nothing really has changed here. But the important thing is that we have to really keep track of our bounds. Here, our bounds are going to be the same as they were in our kind of original integral, right? So we can split up the integrand just like we can with unbounded integration. Right, now this brings me into the next topic, which I think is a bit more important. And so it first is going to have to, I'm going to have to clarify that A is going to have to be less than B, going to have to be less than C, right? And this will be important in a second because given that information, we can take that the integral from A to C of any function f of x with respect to x dx to be equal to the integral from a to b of f of x with respect to x plus the integral from b to c of f of x dx. Right, okay, now so I kind of wrote out this huge long integral expression. There's a lot of stuff going on. Now, what we see in the end is, so essentially what this means is we can split up an integral not only by the sum of its kind of terms, if it's a polynomial, for example, but we can also split up the bounds, right? So that we can come up with multiple integrals kind of over multiple intervals, right? So the integral from a to c, I'm going to draw this out on a graph to the best of my ability. I'm going to draw the math teacher graph right there. Let's say this is a. I'm going to call this B. I should really draw while looking at the board. This is going to be B, and then over here we're going to have C. Right, so A, B, C. Right? If we want to take the area from A here to C, we can do it in one big step by going from A all the way to C, or we can take it in two smaller steps. We can go from A to B, and then we can go from B to C. Right? And so that's what this kind of identity law is telling us. But what's important to note here is the bounds. And I probably should get a different color for this, but what we see is that the integral from a to c of f of x is going to be our larger interval from a to c is going to be equal to the integral from a to b of f of x dx plus the integral from b to c. Now what we see is that the upper bound of this first integral is the exact same as the lower bound of the second integral, right? So that's kind of the important identification to make, right? If you have two integrals, one of which one's upper bound is the other's lower bound, they're really kind of they're measuring two parts of the same whole, right? And now, if you're, excuse me while I erase the board here, you can use this identity to kind of take maybe in a problem you're given some sort of expression that requires multiple integrals, right? But if you notice that integral, for example, is it goes from 2 to 3 of f of x dx, and then plus, and then maybe you have an integral from 3 to 20 of f of x dx. Okay, well, we know that that could be simplified simply to the integral from 2 to 20 of f of x dx. Now, it's important that the integrands match, because if the integrands match, you're integrating two different functions with similar bounds, and that does not necessarily work out. So when we combine functions of integrals of functions like this, our integrands have to be the same, and those bounds kind of have to match. I always like to think of it as kind of like a cross, right? So like, you know, upper bound matches lower bound, so we're going to go from this lower bound up to this upper bound, right? And so there's that kind of like crisscross there, right? And so those are the two big concepts that I definitely should have talked about in the last video. Excuse me while I erase this board. I'm thinking if there's any last thing that I've forgotten. I don't believe so. Everything else I believe I covered in the first video. I covered the, we covered, you know, when you switch the bounds, you simply add a negative to the result of your integral. But I guess there's one thing I should talk about, right? It's that this kind of special case of what happens if you were to integrate, for example, from a to a. Now these are the same a. Now it doesn't really matter what the function is, I'm just going to say f of x dx, right? Now graphically, what this would look like if this is f of x, and this is x, is, I'm going to draw the math future graph. Cool. Let's say this is a. Now we're taking an area from a to a. Okay, cool. So we're just taking this area here, right? And now, so what that would be, if you were to evaluate this, is it'd be, you know, the integral of f of x from a to a, and that end up being like some function f of a minus f of a, which is equal to 0, right? So I claim that any integral taken from one bound to another, but those bounds are the same, if they're the same, then that integral is going to be equal to 0. Now mathematically that works because of this here, because you end up subtracting the function from itself and you just get 0 anyways when you integrate. But like visually, like geometrically, if you look at this, what we're doing here is we're really taking the area of one singular slice, like one single rectangle whose width is dx and whose height is f of x, right? And we're taking that at point x equals a. Now what happens is the width of this is dx, which is infinitely small, and the area of an infinitely small rectangle is actually 0. Kind of weird to think about, because when we do an integral, we essentially take like infinitely many of these areas that are 0 and we all add them up, and then we get an actual number, which works because in calculus you can think of that area as like an actual area instead of just an infinitely thin area, but in reality that's just the sum of many, many infinitely small areas that leads to a whole number, right? So that's also an important identity. If you have this kind of from a to a, you get a value of 0. Your function, the area of that function is 0 at that point, right? There's kind of, there's some more things you can do with integrals, dealing with like symmetries, and like maybe you've heard talk of like even functions and odd functions before. So I guess because we have extra time in this video, I could go ahead and I guess I could talk about that. Maybe save some time in a future video as well. But this isn't really necessary. This is kind of more of like a mathematical trick. So feel free to leave now. Goodbye. If you don't want to learn about this. Okay, so let's take a function, for example. I'm going to draw f of x equals x squared. Looks something like that. Now, and I drew this kind of poorly, but f of x squared, or f of x equals x squared is a symmetrical function. It's specifically an even function, right? Which f of negative x is equal to f of x, right? And that's going to be the mathematical definition of an even function. For example, if I plug in 2 to this function x squared, I get 4, right? But if I plug in negative 2, which would be negative x in this case, I also just happen to get 4, right? And so what happens with even functions is that we're symmetrical about some axis. In this case, it happens to just be the y-axis because we're centered at 0, 0, right? And now, if we were to take the area under this function from, let's say, negative 4 to 4, right? So, excuse me while I erase, I need a bit more space. And we don't really need this space down here. Okay, so, integral from negative 4 to 4 of f of x, which I guess is just x squared, so I should just write x squared dx. Okay, now, a little neat mathematical trick. We know that this could be the area from negative 4 to 0 of x squared dx plus the integral from 0 to 4 of x squared dx. Now, because both of these areas are above the x-axis, they're both going to be positive, and because this function is even or symmetrical about this origin, what we're going to see is that these two areas are actually just equal, right? As such, I claim that this whole integral here from -4 to 4 of x squared will be equal to 2 times the integral of 0 from 0 to 4 of x squared dx, right? And so in case you don't want to plug in -4 to this function, because plugging in like big negative numbers can sometimes get messy when you're evaluating a bounded integral, but 0 is a very nice number to plug in because a lot of times terms cancel out. And so, yes, with even functions, that symmetry allows you to kind of multiply your area by 2 when your bound is kind of that axis of symmetry. And now there's a very similar thing for odd functions, and I'll define an odd function here, and I'll give you an example. I guess I should probably title this, I originally intended on this video just being like me making up those terms and definitions I forgot, but I guess this is kind of like its whole other thing. Right, now, odd function. An odd function is going to be one in which a function which f of -x is equal to negative f of x. Right. So a good example of this is going to be some sort of cubic function. Oh, perfect. Okay, almost perfect. I claim this is x cubed. Right. Another simple single-term polynomial function. If I were to plug in 2 to this function, let's say 2 is right here, I would get 8. 8 would be right about here, right? But if I plug in -2, I get -8, right? So this satisfies, I mean, I have a sample size of 1, but I know for a fact that this this function has a line of symmetry about y equals x, right? If you were to take this part and just like whoop, flip it upside down and around over this side, like that, you would kind of get this other tail end of it, right? And so x cubed is an odd function, and you can try this for any input, and it works, right? And odd functions also kind of have unique cases for integration, and this is just another handy math trick if you'd want to know. Let's take the integral from -4 to 4, again, of x cubed dx. Right. Now, this is, again, going to be equal to the integral from -4 to 0 of x cubed dx plus the integral from 0 to 4 of x cubed dx. Right now, you can test this if you would like, but I claim that this addition is going to be equal to 0, right? Because if this is symmetrical about the line y equals x, this is an odd function, right? What we're going to see is that the area on this side is going to be equal but opposite to the area on this side, because area below the x-axis is going to be negative area. So this negative area over here is going to exactly cancel out this positive area here, given that this bound here is -1 times this bound up here, this upper bound, right? And so with odd functions, this symmetry allows us to kind of work out this identity where the integral of kind of a symmetrical region of an odd function is going to be 0, because all of that negative area is going to cancel out with all of that positive area, right? So I believe that's all I have, actually. Next, we're probably going to power through a bunch of integration techniques that I think are useful to know for computations. There's not a whole ton of like integral theory left. There's a little bit, but I'll be sure to inform you all when we get there about all of that. So thank you for joining me in this kind of like makeup video and learning a little bit about odd and even functions and how they relate in calculus as well. So anyways, thank you very much for joining me. See you later, class. Have a good one.